In this video, we will be talking about optimization. That's where you try to achieve the best possible outcome given certain conditions. For this problem, we will be minimizing length. Two posts, one 12 feet high and the other 28 feet high, stand 30 feet apart. They are to be secured by two wires attached to a single stake, running from ground level to the top of each post. Where should the stake be placed to use the least amount of wire? So we're going to need some variables. So when they say where should the stake be placed, we can put an X to represent how far from the 12-foot post the stake should be placed. On the other side, since we're given that the posts are 30 feet apart, then this length will be 30 minus X. Ultimately, we're going to have to write two equations, a primary equation and a secondary equation. The primary equation reflects whatever it is that we are trying to optimize. In this case, we are being asked to minimize the amount of wire. So the wire is the white. So we're going to need some variables to represent the length of the white wire. So let's see, let's call this Y and Z. So armed with these variables, we can go ahead and write our primary equation. I'll call it W for the length of the wire. And the length of the wire should be Y plus Z. Now we need a secondary equation. In this case, it's going to turn out to be secondary equations, plural. It's going to be more than one. These are equations that reflect other conditions present in the problem, relationships between the variables. For example, if you look at the small triangle, what is the relationship between these three quantities? You might be thinking about the Pythagorean theorem. So, y squared should equal x squared plus 12 squared, for example, right? A squared plus b squared equals c squared. And then we could do that same thing for the larger triangle and get another secondary equation, which is that z squared will equal 30 minus x squared plus 28 squared. All right, again, that's just the Pythagorean theorem. Both of these equations, we could turn y by itself and z by itself by taking the square root of both sides. So if I take the square root of both sides, I get y equals the square root of x squared plus 12 squared. I guess I could go ahead and just put 144. And if I take the square root of the second equation, I'm going to get z equals the square root of x squared minus 60x plus 1,684. I just went ahead and multiplied this out and combined like terms. I'm sure you could do that on your own. The point of having these secondary equations is so that we can use them to turn the primary equation into a version that has only one variable. So imagine that we do the substitution, W equals. So instead of y equals the square root of x squared plus 144. And instead of z, we can put the square root of x squared minus 60x plus 1,684. So this is the equation that we need to minimize. We're trying to minimize the length of the wire. This expression represents the length of the wire. We know how to minimize things. We're just talking about finding extrema. The way you find extrema is you do the first derivative test and find where the function is increasing and decreasing, and that leads you to the point where the function will be at a minimum. So we need to take the first derivative of all of this so that we're doing the first derivative test. So I guess before I do that, maybe I'll show this one additional step. In my mind, I'm seeing x squared plus 144. The square root is the same as the 1/2 power. So I was going to just do it, but I decided to go ahead and show my thinking. Okay, when I'm working this on my own, I don't usually show this step. Anyway, so now I'm going to take the first derivative where I'm going to do the power rule and the chain rule. So the 1/2 is going to come in the front, and I'll have x squared plus 144. Reducing this by 1, I'm going to have negative 1/2 power. But then I have to take the derivative of the inner function. I have to multiply by the derivative of the inner function, which is 2x. So that's the derivative of the first term. Now I need to take the derivative of all of this, and again I'm going to put this 1/2 in the front because of the power rule, and this stuff stays the same. 1684. Again, reducing this by 1 will give me the 1/2 power, but now because of the chain rule, I have to multiply by the derivative of the stuff inside. So that's going to be 2x from the first term, and then minus 60 because of that, and nothing from that. So this is an expression for the derivative. It's just a matter of simplifying this down as far as we can. Well, look, 1/2 times 2 is 1, so I'm just going to have x. And then I think since this expression has the negative 1/2 power, the negative exponent drops you down to the denominator, and I'm going to put it back in radical form. So x squared plus 144. Okay, what's going to happen over here? If you take the 1/2 and you multiply by the 2x minus 60, half of that is going to give me x minus 30. All right, just took half of each term. And again, the rest of this with the negative 1/2 power is going to drop down to the denominator, and I'll put it back in the square root. So x squared minus 60x plus 1,684. So we need to find the critical numbers, and the number one thing you need to do for that is to set the derivative equal to 0. So I'm going to set this entire thing equal to 0. So I have this. Now I need to subtract this fraction from both sides of the equation, which is going to just look like moving this over to the right-hand side and making it negative. So now I have this. Do you guys know the following fact? If I have a minus b, that's the same thing as the opposite of b minus a. I'm sure you already knew that. So you can take a subtraction and reverse it, but then that generates an extra negative. So that will be useful in a situation like this, because if I take the x minus 30 and reverse it, and if I rewrite it as 30 minus x instead, well, that will be equivalent if I generate this extra negative, but then a negative times a negative is a positive, so that will actually cause this entire thing to become positive, which I don't need to actually show at all. Okay, so just remember, a minute ago I had a negative sign there, but then I switched these backwards, and that's why the negative is gone. So I need to solve this somehow. We can cross multiply. Yes, it's very ugly, but we can simply cross multiply. So here I have cross multiplied. I multiplied the diagonals, and I got this. How will I solve this type of equation? I'm going to square both sides in order to get rid of the radicals. Okay, I'm squaring both sides. But that's going to give me x squared now, all right, because I squared that guy. Squaring the radical makes the radical go away. So I'm going to have x squared times x squared minus 60x plus 1,684. Meanwhile, on the right-hand side, I will have 30 minus x squared now, because I'm squaring everything, but the radical will just become the x squared plus 144. So if you distribute the x squared throughout, then this is what you get right here. And if I have 30 minus x squared, I'm about to multiply 30 minus x times 30 minus x. So if you multiply 30 minus x times 30 minus x, you get 900 minus 60x plus x squared. So now I'm about to multiply that times x squared plus 144, double distributive property style. So that gives you all of this. Now I am going to combine the like terms, the 144x squared with the 900x squared, and I will rewrite this all in descending exponential order. So now we have all of this. Let's simplify it down as we compare to the left side of the equation. If we subtract x to the fourth power from both sides, then these are gone. So I can just go like this. Let's add 60x to the third power to both sides since those are identical. So both of these will be gone. So the only thing on the left is this 1,684x squared. Let's go ahead and subtract that from both sides of the equation. So that gets us to here. I'd really like the leading coefficient to be positive, so I'm going to divide everything by -1, change all the signs, and I'm going to put the 0 over here on the right because that doesn't change anything. So we just need to solve this quadratic equation. Turns out that all three of these are divisible by 320. So I'm going to divide everything by 320. And you're to be forgiven if you don't automatically see that everything's divisible by 320. So you might have done this by dividing things by 8 or dividing by 2, and you would just have to do multiple steps, but you'd arrive at the same place. So I could probably factor this, but when I see a large number like 405, I usually just use the quadratic formula. So x is equal to opposite of b plus or minus the square root of b squared minus 4ac, all over 2a. So we have this. Let's just simplify down this radical part and see what we get. Look at that. Turns out to be 63. So that means we have x is equal to -27 plus 63 over 4, or -27 minus 63 over 4. So that turns out to be 9 or -22.5. Don't forget that x represents a distance from one of the posts, so you cannot have a negative distance, so this is not going to be included in the domain. So x equals 9 is probably the answer in terms of the location of the post that minimizes the length of the wire. But we need to follow through and do the first derivative test, setting up the number line and doing test values to verify that this is actually at a minimum. If it is not, then the real answer will be one of the extremes of the domain. Before I show you my number line, let me remind you that we have these two posts that are 30 feet apart. So the placement of the stake on the ground has to be somewhere between 0 feet away from the first post and 30 feet away from the first post. That's why when I made my number line on the left side, I put a 0, showing that that is the end of the domain on the left. And on the right-hand side, I put a 30. That is the upper limit of the domain. And of course, I have my critical number of 9 feet right in the middle. Time for the test values. So I will use a test value of 1 in this interval, and I will use a test value of 10 in this interval. Normally I do this by hand, but I'm feeling too lazy and this is too cumbersome of an expression. So I'm going to cheat and use a calculator. So here I've substituted 1 in for all my x's, my first test value. Let's see what we get. All that matters is that we're getting a negative value here. So let's just mark that off. So we're getting a negative value, which tells us that the function is decreasing in this interval. So now I'm going to do the same thing with a test value of 10. So here's the first derivative with the 10 substituted in. Let's see what we get. Oh, look at that, a positive value. That means the function is increasing in this interval. So since the function is decreasing as we approach 9 and increasing after 9, that proves that 9 is the value that minimizes the function on this domain. So the bottom line is that the stake should be placed 9 feet from the 12-foot post to minimize the wire length.